Hi guys, today I want to share with you a short demo about the evolution of switching power supplies, that how switching power supplies were evolved from linear power supplies. Initially there were only linear power supplies available due to the limited technology that was at that time. However, as technology developed, the switching power supplies starting to evolve, and nowadays you see everywhere switching power supplies. As an example, the mobile phone charger and the laptop adapter that you see consist of the switching power supplies in the flyback topology configuration. And in all the latest machinery and technology, there are only switching power supplies that are implemented due to their high efficiency and lightweight and small components. And the switching power supplies are operated at a much higher frequency in kilohertz range, whereas the linear power supplies that were available initially, that were operating via 50-60 hertz transformer, which was very bulky, and also due to low frequency, the components used were other components used were also very bulky. Because you know that if the frequency is less, the power delivery would also be less, because of the equation power is equal to energy into frequency. So in order to increase the power, you have to increase the frequency of the operating circuitry, because by operating at high frequency, the power output would also be much higher, and so the small components can be used. This is the basic concept behind the switching power supplies. So let's start the today's short demo video, that how switching power supplies were evolved from linear power supplies, because initially there were only linear power supplies. If we see, then linear power supplies consist of the 50-60 hertz transformer, and after the transformer there is the bridge rectifier, then the filter capacitor, and after the filter capacitor there is voltage which is DC but not the regulated voltage. And in order to convert it to pure DC voltage, we have to insert a linear regulator or a series pass element. So let's skip the transformer and rectifier section and directly go to the input filter capacitor, where we had the unregulated DC input voltage. So this is the input voltage, unregulated input voltage, unregulated DC input voltage, and here was the input filter capacitor, and we have to convert it into a pure regulated voltage. Suppose we want 5 volt output, then we will insert a 5 volt regulator or 5 volt series pass element. So this is a regulator, this is the positive polarity of the input capacitor, and suppose it is a 5 volt regulator, then at this point we will get the output voltage, and it would be regulated 5 volt. But the basic disadvantage of using the linear regulator is that linear regulator or linear series pass element is that much higher dissipation occurs in the linear pass element, and that is why we need a big heatsink. So suppose that input voltage is equal to 50 volt, and we want from that 5 volt regulated output. So output voltage we want 5 volt and well regulated, and suppose output current we need is 1 ampere maximum. Then if we calculate the wattage, then 5 volt into 1 ampere, the output wattage that we need to consume is 5 watt. But you know that the regulator is in series with the input and output, so 1 ampere would pass through the regulator, and so it will fetch 1 ampere from the input side. So input voltage 50 volt and current would through input side would be 1 ampere, and the power that we have supplied is 50 watt in this case. And you see we need only 5 volt output, 1 ampere, so 5 watt would be consumed and 50 watt is supplied, so the remaining 45 watt would be consumed or dissipated inside the regulator. So 45 watt is being wasted. So we calculate the efficiency in this case, then 5 watt over 50 watt, it is equal to only 10%. So our linear regulator in this case is only 10% efficient, which is a very less efficiency, very small efficiency. So there is another configuration that you don't use the regulated IC, and instead you make it from discrete components, as was done in the earlier stages of the linear power supplies that were designed at the earlier stages. So let's delete here, we delete here the linear regulator. So this was 1 ampere and 50 watt was there. So here we insert the linear pass element or the transistor. That is connected to the output side, emitter connected to the output side, and collector connected to the input side. And in order to regulate the output voltage to 5 volt, we have to provide the sample reference sample. We have provided a sample of the output voltage to the regulating circuitry. So to provide this sample of the output voltage, we don't need full 5 volt. Instead we can send the small value of this sample. So here is a 10k ohm resistor, and the low resistor is also 10 kilo ohm. So in case there is a 5 volt regulated, then the middle point of both 10k resistor would be at 2.5 volt. So we use a operational amplifier in this case. Here is the plus input, minus input, and here is the output. So we connect the middle point of the both resistor, the sample that we have taken from the output, to the negative terminal, input terminal of the op amp, and on the positive terminal we provide a fixed reference voltage. So to provide the fixed reference voltage, we normally use a zener, and nowadays we can use another IC which is called the TL431. So this is the zener, And if you know the property of the zener, that zener is a semiconductor device that operates in the breakdown region, and when there is no input voltage more than enough, then these and there is a resistor connected in series to the zener, then the zener provides a fixed voltage depending on the specs of the zener. For example, zener, if there is a 3.3 volt zener, then on the cathode side there would be fixed 3.3 volt. If it is a 12 volt zener, then the on cathode side, at this side, there would be fixed 12 volt DC, and it will not it will remain fixed, whether the output voltage whether the input voltage changes from say 30 volt to 50 volt, but the zener voltage at the cathode side would remain fixed. Suppose the zener is of 2.5 volt, then the on positive terminal the reference voltage would be fixed at 2.5 volt, and because input voltage is unregulated, it can be 30 volt, 40 volt, 50 volt, but the due to zener implementation, the positive input would see fixed 2.5 volt. And now suppose that output voltage is so here is the output of the op-amp going to the base of the series power transistor. Suppose that the output voltage is fixed at 5 volt, then the middle point would be at 2.5 volt, and the that 2.5 volt goes to the negative input, and the positive input was also at 2.5 volt, so there would be no output, and whatever the voltage drop was on the collector to emitter, that will remain the same, and we will get the 5 volt. Now suppose that the output voltage has increased to 6 volt, so now the output voltage instead of 5 volt, it is equal to 6 volt. Then the due to voltage divider, the middle point would be at 3 volt, and that 3 volt would go to the negative input terminal, and as you can see that the 3 volt is greater in magnitude, in magnitude it is greater than 2.5 volt, so the negative terminal would be at higher level in magnitude. So if negative terminal it is at higher level with respect to the positive terminal, then output of the op-amp goes to 0 volt or tends to go to 0 volt. So the supply voltage of the to the base would be reduced, and due to the reduction of base voltage, the saturation of the collector emitter would be reduced, and there would be a much higher drop across the collector to emitter, and due to the higher drop across the collector to emitter, because it is no trying to turn off, so due to the higher drop, the output voltage would again reduce to 5 volt, from 6 volt to 5 volt. So suppose the other case, suppose that output voltage is now 4 volt. So due to 4 volt, the resistor divider will produce 2 volt, and that 2 volt would go to the negative input terminal of the op-amp, and because 2 volt is less in magnitude with respect to 2.5 volt, which is at the positive terminal, so now positive terminal is at higher level in magnitude, and the output would of the op-amp would go to the higher level, Due to the output of the op-amp going to the higher level, the base emitter voltage would try to increase, and because of that the current of base emitter junction would increase, and which will try to decrease the collector to emitter voltage, and it will start going to saturation. So the input voltage and current would increase, would pass in a great quantity, and the output voltage would again increase to 5 volt, from 4 volt to 5 volt. Hence this way the regulator, the series pass transistor operates in such a way that if the output voltage is has increased, or has gone to upper limit, then the op amp would behave in such a way that the drop across series pass element would increase, and due to the increased drop, it will rob or steal the voltage from the output, and the output voltage will start decreasing, and from 6 volt it will goes to 5 volt. And in case output voltage is reduced, for example due to the heavy load, it is reduced to 4 volt, then the op amp would behave in such a way that the base emitter voltage from base emitter voltage would try to increase, which increase the base emitter current, and due to that increased current, the drop across the linear regulator, linear series pass element would try to decrease, and due to decrease drop, the more voltage would be available to the output side, due to the decreased drop across the linear regulator. The more voltage would be available to the output side, and the output voltage would again go from 4 volt to 5 volt. So this is how the op amp behave and regulate the output voltage. And there are many op amps available in the market general purpose, like as you have seen in your early textbook as 741 op amp, or nowadays you also see some older version like LM 358. So these are the op amps, but the purpose of drawing the sketch of this linear pass element and the controlling circuitry was that we are going to the evolving stages of the switching power supplies. So this stage is the same as we saw earlier, where there was only a linear regulator, was block diagram was in the middle side. So in the situation is the same. I mean, if the input voltage is 50 volt, output voltage is 5 volt, and output current is 1 ampere, then the output voltage would consumed would be 5 watt, and input power consumed would be 50 watt, because 1 ampere would pass through this series section, and the efficiency is still 10%. So in order to increase the efficiency, the people thought some clever ways. For example, they thought to implement the comparator instead of the op amp. Before discussing the comparator, I will tell you about op amp, that if there is a difference in the voltage level, input voltage, there is a difference in the input voltage level. For example, on a positive terminal there is a fixed 2.5 volt, and on negative terminal there is a 3 volt, then only 0.5 volt difference would go to the output of the op amp, which would control the this series pass element. But in case suppose that the drop is increased on the input side, the same drop would be magnified depending on the gain of the op amp, and so the it would reduce the supply of to the base emitter or increase the supply. But as I told you, that people thought in some clever ways that why not implement the comparator instead of the op amp. So let's see what is inside the comparator. So we'll delete the op amp numbers from here and go back to the same circuitry. However, no, suppose it is a comparator. The pinouts of the normally available comparators and the op amps are the same, and their symbol is also the same. I mean, there are in comparator also there are two inputs, positive input and negative input, and there is a output. Suppose that comparator we use is LM393 or LM339, which are easily available in the market. That operating principle of the comparator is that if there is a volt for 2.5 volt on the positive terminal, and there is 2 volt on the negative terminal, as you can see in this case when there was 4 volt at the output, then the non-negative terminal, the magnitude of the voltage is less, and the positive terminal, the voltage magnitude of the voltage is high. So instead of producing the difference of the input voltage, which is 0.5 volt, which was the case of the op amp, the comparator would produce the full swing of the output voltage. I mean, it would go to full supply voltage of the op amp. Suppose it is 12 volt operating, op amp is comparator is operating at 12 volt, then the output voltage will swing to the full 12 volt. So you can say in this case the series pass element would fully saturate, and there would be a ideally no voltage drop across the series pass element, and all the 50 volt would transfer to the output voltage, right? So let's see what happens and how it would operate. Suppose we keep the sequence original, and suppose that output voltage was at 6 volt, then the middle point of the 2 resistor would be at 3 volt, and due to 3 volt, because 3 volt is at higher magnitude as compared to 2.5 volt, which is supplied to the positive input terminal, so the output of the comparator would swing fully to 0 volt. So here would be the 0 volt, and due to 0 volt the base emitter junction would be reverse biased, and it would cut off the input voltage and the output voltage path, and so the output voltage because of cutting the path, the voltage would drop automatically from 6 volt to 5 volt, and suppose that no, the voltage is reduced to 4 volt. So let's see the scenario that no, here the voltage is 4 volt, then the drop across the middle point of the resistor would be 2 volt. So this 2 volt would be the input of the negative input of the comparator, and now as you can see the positive terminal is at 2.5 volts, so the positive terminal is at higher magnitude with respect to negative terminal, so the output voltage of the comparator would swing to full supply voltage, Suppose that comparator is operating from 12 volt DC, then the output of the comparator would swing to full 12 volt instead of the difference, which is the 0.5 volt. So because of 12 volt, the transistor would get saturated, and due to saturation there would be no drop across the series pass element, and the 50 volt would tend to go to the output voltage, and in this case the output voltage would suddenly increase from 4 volt to 5 volt, right? So in this way, you can see the series pass element would switch frequently at much higher frequency due to rapid action. I mean, if it is a 4 volt, then it is on, and because it is on, so it will automatically become 5 volt due to the filter capacitor. And when it will cross the upper limit, I mean it is going to 6 volt, being turned on, fully turned on, then the signal would be 3 volt through the resistor divider, and so there would be 0 volt to the base emitter, and the transistor would cut off, so the voltage would decrease suddenly to from 6 volt to 5 volt, 6 volt to 5 volt. So this way the voltage would be regulated. But the disadvantage of using transistor this transistor series pass element and the comparator with the in series pass configuration is that there would be very high surge to the output capacitor, because it will turn on and turn off very quickly. So high amount of current would be supplied to the capacitor to replenish its charge. So due to very high surge current, the transistor would also get hot, and the capacitor would also get very hot, and may malfunction or destroy. So to overcome this problem, initially people suggested to insert a small value resistor in between emitter of the transistor and the output capacitor. So if I draw here, this is emitter, and then this is the series pass. This is a small resistor in, you can say, milliohm or few ohm value. So now because of insertion of the resistor, there are two effects. One is that it has reduced the inrush current that is going to the output capacitor, but at the same time there would be dissipation in the resistor as well, because it is also in series, and there would be drop on it due to the resistance of this due to some actual value of this resistance. So it would also dissipate, and it will heat up. So this was also not a solution that was acceptable to the people and the industry. So they then suggested a clever way to overcome this problem. What they did simply is that they, instead of inserting the resistor in between the emitter of the transistor and the output capacitor, they inserted a inductor. So let's see how it behaves when we insert an inductor. So now here is we have inserted the inductor. due to because the we have used the comparator instead of op amp, so it is operating switching at very much higher rate in kilowatts range, maybe in kilowatts range. So uh, now we have inserted the inductor. The property of the inductor is that if there is a DC voltage passing through the inductor, then there would be no resistance to that path, and it will supply the whole input voltage and current to the output side. But if there is a fast switching action at the input side of the inductor, just like in this case by using the comparator, there would be impedance of there would be develop some reasonable impedance across the inductor, and due to that impedance, it will behave just as resistance, and it would stop the inrush current that was going to the output capacitor, so it will not heat up. And the another advantage of using inductor is that inductor is consists of the wiring, copper wire, and we know there is almost no DC resistance of the copper wire, so there would be no dissipation inside the inductor, which consists of the copper wire. So we have solved the dissipation issue as well, but no, there another problem occurred. I mean, the property of the inductor is that in the inductor the current lags behind it. So suppose that transistor was on, so transistor switching, sometime it is turning on, sometime it is turning off, so that the output voltage remain fixed at 5 volt. Suppose that it was previously turning on, and now the 5 volt have exceeded to the 6 volt, so now it's time to turn off the transistor. So the comparator gives the command to turn off the transistor, so the input path is blocked, and but we know that the current in the inductor lags. By saying that current lags in the inductor, that means that current when we stop the input voltage, the current still passes through the inductor, saying that I am lagging, so I have to pass through it, and I will flow until there is zero current through me. So the current continue to flow through the inductor, and it goes to the output side, and through the load, it goes to the ground terminal of the input capacitor, and from there it goes to the positive terminal. From input source it goes to the collector side of the transistor. But no, at the moment the transistor is off, so but the current was lagging, so the end result is that the inductor will start increasing the voltage across it, so that increased voltage would be reflected to the whole path, and the voltage would start increase across the transistor as well, and that increased voltage would be such a high value that it will destroy the transistor. So although we have solved the dissipation problem of the output filter capacitor, and it is operating now at a higher frequency as well, and so the components would be less bulky, and the efficiency would be more than enough, maybe 80-90%. So but now the issue has occurred that the current is lagging in the inductor, and when the transistor is stopped, the current is saying that I have to still go through the path to complete, so that I become 0. So in this case it will start increase the voltage across it, which would be reflected to the whole path, and so the voltage across the transistor would also increase, and it would, because it is in the off state, so that increased voltage would increase beyond the breakdown voltage of the transistor, and it would be destroyed. To solve this problem, the pupil cleverly suggested to insert a diode, high frequency diode, in between the junction of the transistor and the inductor, and the other point of the diode is connected to the ground. So no, by inserting a diode, what happens that when the transistor is on, when the transistor is switching as saturated and it is on, because here would be the total input voltage which would are positive, and if there is a positive voltage on the cathode side, then the diode is reverse biased, and due to the reverse bias action of the diode, no current would flow through the diode, and all the current would pass through the inductor just as normal. But now suppose that transistor is off. So when transistor is off, that current which was lagging in the inductor, that would go through the output load, and from the ground path it has the route through the it would found the route through the diode, and it would forward bias the diode, so it would complete its path through the diode, instead of going through the input circuitry and the destroying the input transistor. So now the series pass element is saved, and it would not be destroyed when it is turned off, and when it is turned off, the lagging current would circulate through the diode and come back to inductor, and so that the current becomes 0. This diode is called the freewheeling diode, and its purpose is to save the series pass element. And as I told you, the efficiency is also increased from 10% to 80-90%. So let's see a scenario that how it is increased. Suppose that input voltage is 50 volt, output voltage is 5 volt. So the due to the implementation of the comparator, the voltage that would pass to the output would be of this form. There would be a fixed voltage. Suppose it is 50 volt. This is the output side, right? This is the output side, and 50 volt. Sometimes it would be 50 volt, and some other time it would be at 0 volt. So would be no in between condition, only the saturation and cutoff. So 50 volt and 0 volt, then again 50 volt and 0 volt, 50 volt and 0 volt. Because there is a output, there is a capacitor at the output side, so that capacitor would average this pulsating pulse width modulation voltage into pure DC. And suppose that the pure DC is average is this level, and which is 5 volt DC. So we would get the 5 volt DC due to the output filter capacitor and the inductor. Inductor would also behave as output LC filter. So the efficiency, how efficiency is increased, because when the transistor is off, the voltage across the transistor would be approximately 45 volt, although the voltage is 45 volt, but the current is 0. So the current is 0 ampere. So the voltage that is dissipating in the series pass element is 45 volt into ideally 0. In ideal condition, the voltage drop across the series pass element is 45 volt and the current is 0 ampere. So the voltage is consumed across in the series pass element is 0 watt, right? So it means no dissipation in the transistor when it is off. And now let's see what happens when the it goes into the conduction stage. So now let's see that scenario as well. So let me drop again the series pass element. Suppose that now the transistor is fully on due to the comparator action. So now the voltage no, because it is fully on and it is in saturation state, so ideally there would be 0 volt across the transistor and the current would be 1 ampere. So again 0 volt into 1 ampere, 0 wattage would be dissipated inside the series pass element. And because there is no dissipation in the series pass element, whether it is when it is on or off, so the efficiency would be ideally in this case efficiency would be ideally 100%. So it is 100% efficient, but due to the physical behavior of the transistor, the efficiency would be less than it, maybe from 80% to say 95%. So we see that in linear regulator the efficiency was only 10%, whereas in the switching power supply it is increased to 80 to 95%. And this type of regulator is now called the switching regulator, and this topology is called the buck regulator or buck topology. So this is the buck regulator. The property of the buck regulator is that the output voltage is always less than the input voltage, just like the linear regulator. So guys, this was the short demo, and we saw that how the linear power supply or the linear regulator, which was dissipating much higher power, and for that purpose we had to use heavy heat sinks. When we shifted gradually by inserting a resistor and then the inductor and then the freewheeling diode, we saw how the efficiency increased to ideally 100% and practically 80 to 95%, and there was no inrush current to the output capacitor, and the output voltage is again well regulated. So this is the advantage of using the switching regulator or switching power supply. And there are two types of basic power supplies. One where the ground path is common from input to output, and these type of regulators are called the non-isolated regulators, just like linear regulators. And the other type of power supplies are where we insert a transformer instead of a inductor in between, and so that the input ground is not connected to the output ground and isolated, and that is used where the input voltage is much higher level, just like a household voltage, and we don't want to create the hazardous situations, so we isolate the output voltage from the input voltage. So guys, this was today's short video, so thank you very much.